Okay, I've just followed a markdown file instead of doing it in any other technique. So you can move that across.
My God, you have so many windows open.
Yeah, I do quite a lot of research.
I thought I was bad.
Like, that's insane.
No,
Wow.
you should see. No. I'm with August here. It's fine.
Really?
I would just split it in multiple windows, though. I
Yeah.
would have 20 tabs here, 20 tabs there, kind of hide it across windows.
I feel like my computer would just
Totally
stop
normal.
working.
This is
That's why I have a gaming computer, you see, just to run multiple browsers.
This is actually quite good for me. I have I usually have at least 4 windows open with roughly 90 different tabs.
Oh my gosh.
Yeah, well, the reason why it's so extensive at the moment is I'm going through a process of creating of doing some projects where I'm developing in business cases for doing particular projects. So if anyone knows anything about that, it's quite a pain and you have to do a lot of research, but at the same time you have to then simplify it down to really simple information. I say really simple, but simple to the point where stakeholders.
Is it Chrome? Is it Chrome? Google Chrome? What's your machine? What's the capacity of your machine? Because this will hog. The Chrome is memory eater. Your machine must be somehow impressive.
Yeah.
It's quite good. Because I actually am a data scientist for my job, and it requires me I have to do a lot of processing, so they've bought me a fairly decent setup.
Nice.
Anyway, going forward, I'll explain. Let's talk about the feature engineering. Unfortunately, since we missed our times last week because I forgot daylight savings time, I have missed on the hours, and as a consequence I probably can't remember all this straight from the top. But essentially, feature engineering is a process of taking predictor variables and making them easier for a model to effectively use, and essentially what this whole chapter is about turning data from just our normal database, our data frame with all the data in it, into something that is actually usable. And that partly comes down from our EDA, or the exploratory data analysis, which is a way of looking through data, realizing whether it's warped in a particular way, whether it needs to follow particular Gaussian structures, or whether it should be just left as it is. So feature engineering goes from process of selecting predictors for one thing, all the way through to mutating our data into a way that's useful. You can use things like change stats, so that might be something like baseline stats comparing something say time 2 compared to time 1, reducing down our data into less complex data, which is what PCA and UMaps do, imputing data, etc., etc. The list goes on forever. But the keys are to really, with your data, is to make sure that you have the right data going into your model, and just making sure you're not putting in too much in there, because we speak about this all the time, but the amount of time you spend processing data is considerable when you're talking about doing large classification models, or doing time series across huge number of models. And you also need to know really what's going in there and whether it's useful or not. Sometimes if you throw in, like, say, 100 variables, it's not only going to slow things down, but it might actually just be causing noisy data. It might have collinearity, etc., etc. Anyway, the point is, where are we so far with our data? With our data, we're the AIMS data. We currently have this code here so far, I believe, which is we have created some log transformations on our dependent variable, and then we've split it using a 80-20 split, which is the initial split function from our sample. And then we've split that into training and test, and then given those two objects names. And that's just an example on the top. We can see that we've got 74 columns, which is a considerable amount of data, to be honest, some of which will actually link together. So when we have a quick skim over this, we see 74 columns, we can see it's almost 3,000 rows, and there are column type frequency 2, 3. Oh, sorry, that's because I selected those. Okay, so in the types that we've selecting in some of our data, we're using just factorial and columns, but there's a mix of it throughout the whole system. And you can also see when we're splitting across sales price, this is general structure, so that's Gaussian with slight outlier over here. And then with one of the things that we do when we're modeling using the base method is we'll do the transformations like the logarithmic base change. We'll do that within the model itself, like over here. And we'll then just tell the model, these are the different elements we want. And this is a particular predictor that we're going to use for the model, and then print it out all at once. The problem with this kind of structure is that it means that we have to do everything within inside the linear model structure, and we're not changing the data beforehand, which means that it's not something that you can easily repeat over, to be honest. So there are reasons for not wanting to do that. So one of the reasons you don't want to do that is because essentially it's not very easy to productize. It's not very easy to repeat it elsewhere, and because you might want to do slightly different transformations each time, but you also might want to program in which transformations are happening and when based on particular criteria. And using tidy models kind of allows you to do that. So in general, tidy model workflow, there is actually workflow for this. Goes as follows, based on documentation I was working with. So I can't remember why I wrote this, but I may as well go over this first. If you're doing something like, if you're using box COTS transformations, don't center the data first, or do any operations that might make the data non-positive, because that does create problems for your workflow. So but if you do need to do something else, do something to the data, you could use the Yo-Johnson transformation instead, because that does allow you to work with non-positive numbers.
I have a question.
Yep.
Oh, okay.
Sorry, Shan. BC to it. We have when you're using a box COTS transformation, I tried to do this on some data that I was working with breast cancer patients, and I couldn't do it successfully because when I'm not that familiar with the process, but also after reading this documentation, I think, correct me if I'm wrong, you have to use you have to pass a model object, like a model matrix, into box COTS.
It kind of works. Basically, what box COTS does is it kind of picks up on the function of the trend and uses that in order to create the bandings around it, or or the error terms. I think that's how I understand it.
Because what I don't understand in this workflow, because log transforms are very the default, but not necessarily used in practice. So everyone I see are using either box COTS or Johnson transforms. In this workflow, I don't really see where it fits, because in recipes, you have to start with pre-processing. So I feel like that would go first. I don't understand the flow.
Well, it would come second. Because you put impute first, so you always want to deal with missing values more than you want to deal with missing values first more than anything else. The reason why you want to do that is because that creates all sorts of problems in your data. So you either want to turn those into zeros, you want to remove variables that are just too sparse, perhaps. you know, et cetera, you have to get rid of you have to deal with the missing values first. You should never leave missing values. You should also never set up your system so that missing values go quietly, because they are they can be quite a problem for a lot of modeling systems. So it's really important to deal with that part first. Then once you want to deal with, like, say, skewness, kurtosis, and all of that kind of thing, the Box-Cox transformation will pick up on the general function of the distributions, and then it kind of penalizes distributions based on the functions that it picks out from data itself inherently. I'm not massively keen on Box-Cox transformations, and I can't remember why, but I do remember reading quite a bit about it before that seemed to suggest that they weren't necessarily the best methods for dealing with they weren't necessarily the best methods statistically for dealing with distribution problems. If I can find the research, I will send it across to chat, but I can't remember off the top of my head why it is that I don't think about using Box-Cox as the best method. Some people prefer it. Okay.
Thank you.
No worries. Okay.
Yeah, I have a quick question.
Yeah, go for it.
All right. Okay. So the other day, my question is, if I have values which consist of, for example, negative, and I want to log transform them. So I tried in the other day, like, transform some values, but include some negative. But I understand I cannot log transform with negative values. So how can we deal with such situation?
You use the Johnson transformation instead. It can deal with negative values. I think you can log transfer. You sure you can log transform with negative values, can't you? It's just you can't use Box-Cox with negative values.
No, log transform. I think, I don't know. I try using taking log transform for negative values, but they say you can do that.
It says,
No, you can't take it.
Yeah,
you can't
you
do a
can't.
negative.
Oh, okay.
They're at a constant. That's like a way to handle it.
If you know what your most negative value will be in the data set, you can add it all on, I guess. But it's tricky.
Yeah, because, like, I have values that ranges from 1 to 10 and -1 to -10. So I wanted to take log transform, and I don't know, like, adding one constant value may not solve the problem. So I don't know if there is any way to take log transform of negative predictors.
I think it's something that you probably just have to research a bit further. I mean, exploratory data analysis is often about finding out what your data looks like, how it's working, and then deciding how to apply to it. If you, you know, there's the other question of, are there meant to be negative values there as well? It really does depend on your data. For instance, in a lot of data I deal with, you know, if there's a negative value there, it's
It
not
is
meant to be
Yo
in the data set.
Johnson. So
yeah.
I'm sorry, August. I'm reading the vignette for recipes step Yo Johnson. There's a function for it, and it specifically states it's similar to Box-Cox, but does not require the input variables to be strictly positive. So there you go.
I guess they both require positive, but Yo Johnson allows you to use negative.
Anyway, so if we're going to carry on with the tidy models workflow, the general advice is you impute first, you then deal with your distribution issues or skewness, kurtosis, etc. Discretize. I don't really know what that is, but that was something that they had mentioned online, and I can't remember why I put in there. The next thing you do is dummy variables. Now, we'll go into that a bit more a bit later, because sometimes the problem with dummy variables is they expand your database. And then the next thing you're meant to do within the recipes system is to create your interactions, and then you do your normalizations, and then finally you do multivariate transformations. And what that is basically dimensionality reductions. Well, to some extent. Although it doesn't necessarily mention lasso techniques, but I suppose that's slightly different. Anyway, so as you can see here, what we have is the same system going on. So we create a recipe rather than making all of our changes within the linear model itself. We create a recipe for the changes that we want to make. So what we do is we start with the recipe technique. We tell it what the model is, as we did in the last one. So sale price as a function of neighborhood, as a general living area, year built, and the building type. And then we also give it the training data set. Then we pipe that in, that's what that is, into the step log function, which is where we do our base 10 log transformation. And we do that to this data set here, which is general living area, because we already know that is skewed. We then finally do the step dummy. And what you see here is this function called all nominal. You can apply other kind of techniques as well, where it's like all numeric as well later on. What this gives us, once we have created this this object here using the recipe, is it puts out this output. So in the output, we can see that we've got one predictor, sorry, outcome variable, and 4 predictors, and that the operations that are set on this data are a log transformation on the living area, and we've created dummy variables for all nominal. If you had specified particular variables, it would list those. So that's what's going on there. Now, as I mentioned before, the problem with dummy variables, and unfortunately I haven't actually managed to get a bit of code working that I was using before, but essentially we know that if you look at your contrasts, you have a load of zeros and ones created in a dummy data set that's hidden in the background in R. So when the linear model function is called, what it does is creates this contrast matrix in the background, which is what it uses in order to see which bits of data are associated with a particular categorical variable level. Now, because we're doing that in here, we aren't calling that until later on. But what it does do is it changes the data set. Now, what that can do is it makes it very, very, very wide. So a prime example of this is in the UK, there are 1.7 million postcodes. Even if you are using a snapshot, you're still using thousands of codes. In America, there are something like 400,000 zip codes, apparently. So that's going to, again, expand the width of your database. If you expand the width of your database, it's going to increase processing time and make your modeling much more difficult. So what can you do to get around this? What you can do is you can either use embedding techniques or hashing. Now, embedding techniques basically, as I can read off here, encodes categorical data as multiple numeric variables using a word embedding approach. It's originally intended as a way to take large number of word identifiers and represent them in smaller dimensions. So essentially, if you know what a PCA is, which is working with numeric data, it takes a load of variables and squishes them together in order to make them usable to the model so that the model's not too wide. And that's essentially what the embedding technique is doing. It's giving a number to these levels, but reducing them down into smaller number of columns. Hashing essentially does the same thing, but uses cryptographic methods. I'm a bit more of a fan of hashing than I am of using the embed technique, but I've not really used the embed technique before, so I can't say how good it is. I think you have to test between the different two to see how they work in your models, which is where the tidy framework actually works really well, because essentially what you'll be able to do is try the different methods, try hashing or embedding, and then you could compare them together to see which one gets you the better results. Differences with hashing is that you can specify the number of columns you want it to go down to. So what that would do is, say you have 400 odd levels of your categorical predictor, you can reduce that down and say, well, I want that in 15 different columns, and it will use cryptographic methods in order to reduce down what that information means to the data, to your modeling system. Right, so here's the other important part. So far, after having created our recipe, regardless of what steps we've used or not, we actually haven't changed our data at all. It's not until we apply the prep process that this happens and the transformations are applied. So as you can see, the recipe applies the changes that were specified to the pre-processing data set or the training data set. It's also a more compact syntax, and it allows us to see exactly what we're doing, where we're doing it, and also I presume we could put it into an if-else statement and make some put some conditions in there in order to decide what's happening if we're putting in a completely different data set.
And I have a question, please.
Yeah.
So for the recipes step, I don't know if any of you all have used it or use it regularly or on your own data. But when I did, I got hit with an error about column name receptor. This is my column. It got dummified. Receptor subtypes. This is for breast cancer. So basically, it's like ER negative, HER2 positive. But they became duplicated because of symbols, and it told me to use .name repair to specify this repair, but I don't know what that meant. I was just curious to see if anybody has come across this error before. And then I have a subsequent question on prep. It's a little bit more theoretical.
I've come across that same error. Pluses, minuses, or any kind of symbols in your column names will throw that error, because a lot of the algorithms need normal column names to work properly.
Right.
So all you have to do is change your column names to more standard column names. Like you could just write out plus, or write out plus minus, or something. Or there you go. Yeah, janitor clean names is another one.
I use janitor clean names for my column names, but this is the values of one of my columns. When it was dummified, it had plus and minus in them. So that I was trying to see if there was an alternate way for me instead of me having to manually change each value of this column to remove the plus and minus symbols. But
you could just use G sub or string replace.
Right. And actually write out positive and negative.
Yeah, like P or N.
Yeah.
And something like that.
Okay.
Yeah, and it's just a one line of code.
Okay. I was just really curious if it's just me or anyone else has had this issue. But for the prep step, I'm a little confused also, I guess theoretically, on he writes, so they write in the book, if you go into the book, it says, remember when it says, sorry, the bake function can apply to any data set. To get the process version of the training set, we could use bake and pass in the argument AIMS trained, but as previously mentioned, this would repeat calculations that have already been executed. So why would we need prep in this instance? Sorry, I might have fast forward, but you said prep and I already thought bake.
Okay, so bake's more what you're doing when you're applying your data to, it's more really what I think about when you're applying the data for prediction or for later on once you've got the model. But the question is, the thing is if you're not really using it for prediction, and you also want to retain the data in order to explain what your model's talking about, you need to use retain, because Otherwise, you've transformed your data and you've created a model, and that model is meant to be being used to predict an outcome variable based on the data that you're throwing into the model, because that's essentially what models do. They inherently are there to predict based on the predictors that you're using. So when you throw in a load of data, say, well, I've got square footage of this. So if you were giving this data set to a estate agent, you would say, well, I've got a house of this type, I've got this kind of square footage, this is neighborhood it's in, what price should it be? And then the model will go, that's the price it should be. That's what the model does, and that's what Bake is essentially about. When you throw that data in there, it predicts.
Right.
So if you want to then investigate the model that you've created rather than using it for predicting, you need to use the retain part, and then you can investigate that data. Does that make sense?
I think so. I'm still a little bit confused on the prep step.
Think of it like this: when you run a model,
Right.
when you run a model using a linear model, right? When you press and execute it, don't assign it to anything. You just execute it. That is running everything that you told the model to do. So if you've got log transformations in there, or if you told it to use interactions, then it will apply all of that at once, and the contrast coding and everything else. And that's what it does. It creates all of that, but it's not doing any prediction. You have to then use a predict function to predict on it. And you have to use a summary function to look at what's going on within the model. But the difference is because of how tidy models works, you need to use the bake function to do that, I believe.
Okay. Okay, so we have by default retain is true in there by default. So you don't, because in the example in tidy models book, in the example, if you go to the book, they pass in a null data for new data. So nothing gets returned.
It means that it's not going to do any predictions on it. It's not going to, it just means that it's going to return the data, or sorry, the model that you've built essentially, and all the parameters based around that.
I see, okay. Okay.
Well, I mean, to be honest, that's the next section we're looking at, so that's actually quite handy.
I'm sorry, I skipped forward.
No, it's okay. It's actually to talk about in a discussion, isn't it?
Yeah, I have a quick question, please.
Yeah, go for it.
So in this prep, we do specify the data. Can we use tidyverse style where we provide the data like MS trend and use pipe and call the prep? Because I can see that I tried to use the first step where we use the recipe, and I call the data first, the MS trend, and use the pipe, and now call the recipe function without providing the data inside the recipe function. It works. But when I call in the prep, I call the data first and then call use the pipe and call the function prep without providing it, but it didn't work. So I'm curious why it works in the previous one in recipe, but it didn't work in the prep.
It's the order of arguments to prep. You have to use the dot with a pipe to choose where to put the whatever is coming out of the function preceding that you were piping from. Whatever the result of that function is has to go into the appropriate argument slot in the function you were piping into, and you can do that with the dot.
Okay.
Yeah.
So you mean when I call the data amis, I need to put dot amis, or what do you? I'm quite confused.
So if you think about a pipe as like input goes into function and then output goes through the pipe to the next function.
Yes.
The default behavior is to stick the results from the previous function in the first argument of the second function.
Okay.
And in this case, it sounds like what's coming out of the pipe is going into that first argument slot, and it doesn't belong there. I think it's probably you want to put it in training, so you would have to write like you would have to put brackets around it, put prep simple aims / training equals dot, and then the rest of your arguments, because you want the results coming out of the previous to go into that second argument instead of the first argument slot.
Right, but the recipe also, the data is not at the first argument. If we in the book is the last argument, the data, but it works if you provide the data. I don't know, what does that mean?
Let me look at what comes out of both of those.
The recipe function.
Yeah. All right, let's see. Okay. So recipe puts out the recipe object. And then prep takes the recipe object. So you said prep errored when you piped it into prep?
Yeah.
All right, I'll look at this. You can keep going, August, and I'll have an answer in a minute.
Yeah, no worries. Thanks, Stephen. Right, so we've just been over this section actually, so which is actually really useful because it's probably easier to, like I say, to discuss it than it is to actually to present it in this way. But prep you can think of as executing the recipe. So you apply that to your training set and it creates your model, as it were. So what we can see above is in the above, we're missing the original data, which has been altered or transformed. So what you want to do is you can, by default, is we want to retain the data. The reason for not wanting to retain the data is because if we do retain it, then it can be pretty large, and it, as we've discussed before about the amount of data that our computers can hold, by allowing ourselves to keep hold of the data when it's not necessarily useful for us, we are putting more demand on the systems that we're using. So sometimes you just want to drop that data off because it's not particularly useful, and that is particularly the case when you're just modeling to get your, for instance, predictions, and you're not trying to use it in order to explain a model. That's where your difference comes in. What do we have here? So when we've done our prep, we get our simple aims. And the simple aims we can see here. So here's a data recipe and outcome predictors 4 again. And the training data contained 2,346 points with no missing data. If there was missing data, it would tell us. And then it tells us the operations that we applied. And it tells us, unlike where we had prep, it tells us where the dummy variables have been applied. So we can see that we've got neighborhood because that's a categorical variable. and the building type is categorical variable as well, which means that we have expanded the width of our database with dummy coding for those particular things.
Does anyone know how to see the dummy variables, the encoding done?
I was looking at it before. I think you can probably look at the data set.
Because I tried to look through, because you end up getting a large recipe, and actually you have to run, I think, when I just run sorry, I'm gonna say the name I did, simple breast, if that's the name of my data set. I end up getting a just a list, and it doesn't show my dummy variables. But after I run it into prep and assign it again, as I've done in the example, so they assign prep back to simple aims, then I end up getting a large recipe object, which includes my breast, my what would be my aims, categorical dummified variables. Maybe this has something to do back to Sham's question about piping.
I
why it wouldn't work.
I can't personally see it here because I've run the markdown, so I can't actually do the code individually. Give me a few seconds. I think
I found it now. If you actually run the prep step, and you are returned with a large recipe element, and it's actually, if you just do simple aims, in my case, simple breast, $, template, you get all the values. So, okay, I just answered my own question.
Oh, okay.
So yeah. But you have to actually run the prep step and assign it to be able to see what has been done. You know what I mean?
Sorry, say again.
So you actually have to run the prep step and assign it. So if you actually were curious to see what's happening in the background, otherwise it's just going to do it and retain it.
Okay.
Are you asking like how to see the data that it turned into dummy variables? Like you want to look at the data set?
I wanted to actually see the data set, but what they have done in the book is they just ran prep and then they did nrow. Oh, sorry, that was bake. Sorry, I am just like all over the place.
That's just...
Anyways, but yeah, once you assign it back, once you've prepped your recipe, then you can see all of the stuff that's been done.
I think the interesting thing here is, can you see my my studio?
No.
Just your browser.
Oh, which one is it?
If you call bake on your prepped thing with new data equals null, it'll give you your data set with all the dummy variables.
So maybe I'm wrong about this, but my understanding of the prep step is that it just learns the things it needs to know from your data to then execute whatever transformation you're doing later. So in this case, if you're making dummy variables, it'll learn the levels of your factor that you're dummifying, but it won't actually transform it until you bake it. That's my understanding. So then if you were to go ahead and apply that recipe, bake it on another data set, it would expect those levels that were in your in what you prepped it on. If that makes sense.
Yeah, that actually does make sense, Kevin.
Because maybe I'm wrong, but I don't think that the prep step actually does any sort of, I don't think it changes your data set at all until you bake it.
Okay.
Like if you go to an August slide in that in the outcome, like when he kind of viewed the properties of the prepped recipe, it just says log transform trained, dummy variable trained. And so what I think that means is that it's just learning what it needs to know about the data to then actually do the dumbifying in the next step.
Right. So you see on his screen on line 128, he's reassigning simple aims back. It's been the prepped version of simple aims back into simple aims. And so I think it does do the things that has been, the steps that have been asked of it from the recipe step.
Yeah, I got to say, Ken, that the data that I've just pulled out there is so this is from this, I pulled it out from this function here. So I got up to this point, and then I've just pulled out the whole variable, and you've got a series of ones where the data probably ties up with it, I imagine. So it looks like it's actually done the contrast coding.
Okay.
Maybe when you print it, I don't know, that's confusing to me. Maybe when you print it, it's baking it so that you can see what it would look like. I don't know. It just, if that's true, then I don't understand the difference between prepping and baking. You know,
I've got to say, I did struggle with this one too. So I thought that baking was when you finally made the model, but I came to the conclusion that actually you're making the model originally with prep, and then bake is really more for applying it for when you want to do your kind of forecasting, predicting. I could be wrong. I think it makes more sense. I mean, I think it makes more sense the way that what Kevin's saying, but
it does. But when you actually see it, this is where my confusion came in. What is explained in the book, and when I actually do it in practice, it kind of contradicts. And this, I look at the output of simple aims after you've prepped it, and it's done all of the steps. So this is where my original question comes back, and it's like, okay, so I kind of have a confusion on prepping and baking.
Okay.
Where does that line?
Well,
the line?
I think we have a problem with our mental models here, and that maybe we need a bit of clarification elsewhere. But I mean, it makes sense both ways. I mean, I think Kevin could be entirely right. It could just be baking it so that we can see what it would expect from the data that goes in there, because it does already have that training data linked with it.
can you just, maybe it would be helpful, could you open simple aims in your environment tab, like in the actual object, and just see, I think it's right there. Let's see it, or yeah, you just expand.
Oh, sorry, yeah.
Last one there. And just see what the, like, or view it.
Yeah, see, so you have a, let's see, you have a level called template. See how it has 2,346 by 35, and really we only had 4 or 5 predictors. Those 35 have been dummified. So those are all the levels of neighborhood.
So it does have the transformed data in the object.
It appears to, yeah.
Right. Then I'm totally confused about what the difference is in those two steps. But
I do remember reading something that no, do you know what? It's about a week ago. I can't remember off the top of my head. It was just something about sometimes you can skip certain steps because some things will just go straight from the recipe without doing prep or something. I can't remember off the top of my head. Maybe I'm talking bollocks. Yeah. Sorry, shall we just carry on? And hopefully someone else can provide us with an answer later on as to whether I'm completely wrong in this.
Wait, you actually, sorry, August. So last time there, I think either Emily or somebody put a post to Julia Silge's blog on the mountain climbers, and she, in her example, if you read her blog post,
I do.
She only uses recipe, and then she skips down to, she does a random forest model, and then she skips to the
bake.
to the bake. So she basically says, we're going to use this recipe in a workflow, so we don't need to stress a lot about whether to prep or not. If you want to explore what the recipe is doing to your data, you can first prep the recipe to estimate the parameters needed for each step, and then bake to pull out the training data with those steps applied. So like, it's more, she makes it sound as if it's kind of like, if you're curious, you can run prep.
Yeah, but in a few cases I've worked with tidy models, and like since I discovered it recently, those later steps of like once you have a recipe and a workflow of like fitting and predicting, it just kind of does all of that prepping and baking behind the scenes. Like you don't have to explicitly call it, and so maybe that's why I was confused here, because you don't really have to do it in a lot of cases. It just kind of, the higher level functions kind of do it for you. But
yeah, I've got to say, I can see where the confusion is, and also that if you do read Advanced R or go through a book group from that, you'll soon start thinking about R in a very different way, because things about like quasi quotation, so meta programming, become really kind of quite convoluted and complex. But it's quite important to know when something is being captured and when it's being executed. And the way how I think about prep is that it's kind of like almost like creating a quoted abstract syntax tree that can be then applied at a later point, so that you can then chop and change bits within that abstract syntax tree. It's quite mouth twister. Anyway,
I have one thing to add there.
Yeah, go for that.
Possibly resolving why it's confusing as to the differences between prep and bake in this particular example is it looks like prep is already creating those dummy variables.
Yeah.
Just because of the type of steps we're using, because I've definitely used recipes with other steps like centering, and it doesn't go ahead and compute it. It just computes like the mean and the standard deviation, and that's all it actually holds in the recipe, like after the prep function. And then when you hit bake, then it actually goes through and centers everything, and you get the actual data. So I think it just depends on what steps are involved as to how much computation it does in the prep step.
Okay.
Yeah.
Well, that makes sense then, because it's kind of like, I suppose it's processing efficient, isn't it? To do some parts first and some parts later.
Yeah, I think it's optimized for that. I don't know what the reasoning is, but I think that's what they were going for.
but then it's a mixture of everyone's mental models.
Yeah.
Right.
Yeah.
Oh, this is mind-bending. This makes Monday nights seem easy at the moment.
I just posted a Stack Overflow about this exact question, and Julia Silge is actually the responder, the answerer. So we can take a look at that after, but I don't really spend too much time on it.
Okay, no worries. Julia is part of the Slack group now. She'd be interested to see what she has to say. She's usually pretty on it, to be honest. Right, let's have a look. So once we've done simple aims, it might have made some stuff, it might not have done, hard to know. But what we can do is we can use tidy, which is from tidy R. And is it from tidy R or broom? Oh fuck, I can't remember. Sorry for swearing.
Broom, I think.
Anyway, and that allows us to turn our prepped recipe into a table, so we can see what's going on there. So we've got
I was
these
just looking at your
operations.
browser, August. I'm sorry.
Yeah, sure. I'm trying to fight with my eyes to look at it.
Sorry, I've not swapped back across. Let me just share the screen instead, it'd be easier. Right.
I'm sorry to do for disturbing you with many questions. We are slowing down, but it shows we are really following and understanding the concept. That's why we asked.
Yeah, I mean, that's the most important thing. It doesn't really matter. Look, I've got a bit more time, so it doesn't really matter if we're a bit slower on this. And
we can always split it.
Yeah, it's really important to remember as well, like feature engineering is the key to good models, or without a doubt. You know, if you talk to or spend any time listening to any data scientists who are more at the modeling end of things rather than the creation of, like, say, packages that we use, they will tell you that features are what are important for prediction or for categorization. So I believe what Andrew Ng, basically, there's a quote from him that basically is saying, like, you know, feature engineering is really important. There's this thing in Python called feature tools, which I asked the group about not too long ago. And it kind of creates its own features, but I am very skeptical as to whether that's very good, because Max Kuhn made a really good point the other day when I was watching a video that he was in. And he was saying one of the things you can't really do very well is to automate feature engineering. You can't, it's really, really difficult to automate. And the reason why it's difficult to automate is because it requires knowledge and expertise, and you can get a computer system to do it. And we often get, in my company, systems to do a lot of automatic processes. But the problem is that they will do strange things that don't make sense. And then you end up with these really bad predictive models. Anyway, I'm going off on a tangent.
Neural network deep learning automate feature engineering, right?
Neural
network.
I
Deep
mean,
learning, you don't need that.
I've got a lot of belief in the ability of statistical models to do a lot of things. However, there are things that they are not very good at, and that is because they are not intelligent. They're not intelligent at all. They are like stupid children.
Okay.
You know, if a child kept banging its head off a table, it wouldn't keep going and banging its head on the table. That's what neural nets do. You know, you can process it, you can do loads and loads of stuff and work to it to help it improve, but they still bang their heads off the wall when they hit a particular problem, and will continue to do so. If that makes any sense at all. Anyone who does modeling knows my pain. Right, anyhow, if you do simple maintenance and tidy, it's a way of looking at it's a way of looking at the recipe in a tidy way, and it basically gives you data as to whether it's been trained. So actually, what Stephen was talking about there was whether some things become trained after they're prepped and some things might not be. It says true or false here, and then it tells you the type of coding. So in this case, it's dummy coding. So we haven't used embedded. We haven't used hashed. And then it's got this ID here. I'm not entirely sure what that's for at the moment because I didn't get into that part. But essentially, this is, if you had, like, say, 20 different steps, you'd be able to look at it here and see what happened and see what processes have taken part or not. Now, the next part is to bake. And the baking then applies everything to your data set, and it also allows you to do your prediction at this point in time. So as was mentioned earlier, you can put a null in there and it will give you back basically your model, and you can look at what's with the original data set and look at what's going on there if you want to investigate that. If not, you can put in your test data set, and then it will apply the information that it picked up in the pre-processing step and apply that to the new data. And you can see here, it's picking up on the same kind of information. And also you can see what dummy models were put into it. If you can see that also when it's created the dummy sets, it's also added neighborhood and then added this, this underscore there. And that's just to distinguish it and tell you this is from this particular variable and these are the levels from that variable. Which you can go searching through and look at yourself if you wanted to. So if you do tidy, and we've called it, did we call it testx? Where does that come from? I don't remember creating that. Oh, sorry, yeah, sorry. When we baked it, we called it testx. So that's test explicit in this particular case. And then when you've finally baked your model, you can then use tidy and it will pick out all of the different elements of the data frame. So instead of, it's not a summary of the model, it's telling you all the elements in the model data frame. I believe, and put them in a tibble. If you want to look at the original data, as we mentioned, you can put null in there and it will pull out your data, and that's why it's got this. And the reason why it says this number is because that's telling you how much data has gone in there, because the test set has a much smaller amount than the training set. Now, if you want to look at the encoding categories, we can see when we look down, we've got all these numbers in our neighborhood. This is problematic. Oh yeah, I've already discussed this. This is problematic because it increases the width of the data set. So that is one issue there. It's highly probable that some of these features won't be important to the model. So what you can do is you can dump them in a step called step other, and that basically allows you to link them all together. So here you go, right here. If we take step other and then choose a variable neighborhood, and then put threshold 1.01 in. This is why EDA is really important, because when you see things like this, you want to just, for instance, drop off those ones and put them all together. It makes it much easier for your model to predict more accurately. Then another thing that we add into the model as well is if we've got interactions. So in normal models, we have to actually specify the interactions. We can see here that there's different levels depending on what particular building type we've got in. So the way how the model moves, or the linear function has moved, depends on the building type. So we want to add in also something like step interact, which I haven't put in this bit here, but is the reason why this bit exists in the book.
1 sec,
Yeah.
I just want to blip in because I am conscious that it's Monday morning for Janita, and she might have somewhere to go.
Oh, okay.
Janita, can we keep going, or do you want to split this into another day? Do you have something you need to start doing with your morning, or are you there? Yes, we can keep going. Okay, cool.
I actually would like to propose that we can continue, because I have more questions that I don't want to take a lot of people's time on.
Well, I don't think there's much more left, really. So
Okay.
more than welcome to ask additional questions, but because the last part are, you can add something in like step interactions, and then we're going to talk about splines, and then briefly about data reduction. But like that's it. So we've already discussed interactions. You have to specify them using like step interact. Sorry, because I cut a bit of code out, I've moved some stuff around. And then there's also splines as well. Do you guys know what splines are? They are so you might call them polynomial or degrees. Basically, what they do is if you're using, like it says in the book specifically, but if you're using like geom smooth, you see the linear line move and it curves. So what you're saying is how many curves or how many degrees of freedom it has to move around. So as you add more in, it allows the line to move more. The problem is if you're adding too many splines or too many degrees, you get overfitting of your model, which means it's not generalizable in the future. So for instance, you might have 2 splines, seems okay, it's not great. But for instance, in this case, 20 looks good. I would personally go for 5 because I think it's because I always think simpler is better, but that's what this poor fit is about. So basically, when you see something about splines, it's all about how to change a linear model into something that moves with the data a little bit and actually is better at actually coding that data. So you can see here, we've got, so this is our recipe at this point in time. We've got step log, we've got step other. That is in order to reduce. So when we put threshold into step other, that reduces down anything that is less than 1% of this variable will be categorized together into an other category. We have done step dummy, which turns all our nominal variables into dummy coding. We have step interact, and here we say as a function of this variable and anything starting with this. And the reason why starting with this is because that is a categorical variable that has been encoded in dummy coding up here. So we have to add this bit here to say anything from greater living area interacts with anything that starts with this. And then finally, we have this element here where we've got latitude, and we know that latitude is not a linear function. So we decide based on visual inspection in this particular point to use 20 degrees. And then finally, that's the end of our recipe. Now, there are some other points to be made quickly, because I haven't put them in there properly, because this is from one computer and not the other, and I seem to have lost bits. But you can also, the final step in a lot of the feature engineering is PCA, or dimensionality reduction. So what that does is, if you've got loads of numeric variables and you're using those in order to try to help build yourself a model, as I mentioned before, too many predictors in a model slows down the model and also can actually make it overfit. It can be it can sometimes create too much noise, and also sometimes you don't need that many predictors. Sometimes things are, you got collinearity between variables, and sometimes it's better just to reduce them all down. So you can, for that, you can use a principal component analysis, or if they're non-linear, you can use a UMAP function. I believe there are other techniques. There's one I was thinking of particularly for categorical variables, but never mind about that.
TSNE.
That's it. Oh wait, no, TSNE is almost like UMAP, isn't it?
Yeah, it's pretty similar. I was just wondering.
Yeah, I think TSNE is what you'd also use for UMAP, but UMAP's like a better version of it. Might work with categorical predictors. Anyway, the point is, you sometimes want to reduce down your features, just like you do with the categorical levels. Sometimes you need to reduce down numeric data as well. You can also use lasso as well. I believe there might be a step lasso function as well in the tidy model framework. I haven't seen it, but at the current point in this chapter and what I've looked at so far, PCA is quite common. I've seen lots of other people using the UMAP function because it's really good when you've got nonlinear data, and you often will have nonlinear data. So it's a really important step just to reduce down the variables and to help the processing times. And that's kind of it for feature analysis. For feature engineering. It's long, it's complex, and there are lots of things you can do to data that we have not covered. These are what I would call the basics.
Thank you. That was a lot.
it was surprisingly a lot. Yeah, I mean, there's so much to do. I can't stress highly enough how good it is to watch other people who are data scientists do feature engineering. Like if you watch Julia Silge's Tidy Tuesdays, get some great stuff off there. Dave Robertson as well, he does stuff online. You know, it's great to watch him do things as well. And I've mentioned before that, but business science, Matt Danko, like he does some incredible stuff and like some really complex stuff, which is really good for businesses, but also shows you how to use tidy models really, really well. He uses that quite a lot. So YouTube's a great place for it. There's also a guy called Andrew Kanch, I think, and he also does some amazing stuff. He's got a video on tidy models, which he goes over like the Titanic data set. Basically kind of explains how you can use that in order to get better features out of it. So feature engineering, what is it? It's a means of making your data better, cleaner, and also either expanding it or decreasing it in order to build better modeling systems, essentially, which is what helps you to build and predict.